the phenomena which is based on total internal reflection. You know what is total internal reflection? When light goes from denser to rarer medium, an angle of incidence be greater than critical angle, then light is reflected back in the same medium. This phenomena of reflection back light in same medium is called total internal reflection. And in this case, in total internal reflection, 100% light energy is reflected back. Unlike in case of reflection from mirror, some energy is absorbed by mirror. So 100% light energy is not reflected by mirror, but in case of total internal reflection, 100% energy is reflected back. So there are certain phenomena that are based on total internal reflection. So we're going to see one by one. First is working of poroprism. Working of poroprism. What is poroprism? It is a right angled isosceles prism. It is a right angle isosceles prism, that is called poroprism. It is used in periscope or binocular, and it is used to bend light by 90 degree or by 180 degree. You know, this prism is made up of glass whose refractive index is 3/2 or 1.5, and this is air. In case of air glass interface, critical angle is approximately 42 degree. So if angle of incidence is greater than 42 degree, then light is internally reflected, and phenomena is said to be total internal reflection. See, if a light ray incident on this border, on this interface, it is incident normally, so angle of incidence is 0. It means it will go undeviated, and then it is incident on this face. On this face, if it is normal, then this angle will be 45 degree, and it is more than critical angle. So this is angle of incidence on this second face, and this angle is more than 42 degree. Hence there is total internal reflection here. So light is reflected and get incident normally on this surface, so go undeviated. So in that way, this ray internally reflected here and goes like this. Similarly, ray from here goes internally reflected here and goes like this. So image of this object is formed here, and here you can see that light is reflected, bent by 90 degree. Similarly, in this case, total internal reflection occurs at this point, at this point, at this point, at this point. Here there are two total internal reflections, at this face and at this face, because when light goes from glass to air, here two angle of incidence will be 45 degree, and that is more than critical angle. So there will be total internal reflection here, total internal reflection here. So here light is, you can say, deviating by 180 degree. This object, this is image. Here too there is total internal reflection here. Light is going from glass to air, and angle of incidence is more than 42 degree, more than critical angle. So total internal reflection occurs here, and light goes like this. So image of this object formed here. Now we can, bend light by using mirror, but why I am not using mirror here? I am using prism. It is because when reflection occurs through mirror, 100% light energy is not reflected. Some energy get absorbed by mirror, but in case of prism, 100% energy is reflected because of total internal reflection. That is what written here. Mirror can be used, means to reflect light, you can use mirror, but intensity of image when prism is used is large because of total internal reflection as compared to mirror, because in case of mirror reflection occurs, and in simple reflection some energy is being absorbed. In total internal reflection, no energy is being absorbed. That's why in binocular or periscope, instead of plain mirror, we use prism. So that is one application of total internal reflection. The second application is shining of air bubble in water. Suppose this is water and this is air bubble. Refractive index of water is 4/3. So sin C is 3/4. Hence, when C is calculated, it is approximately 49 degree. It means when light goes from water to air, an angle of incidence in water is more than 49 degree. That is more than critical angle. The light is there is total internal reflection. And because of this total internal reflection, this air bubble shines. So shining of air bubble inside water is because of total internal reflection. Third use, sparkling or brilliance of diamond. Critical angle for diamond is 24 degree, and diamond is cut in such a way so that when light try to come out of diamond, angle of incidence inside diamond be more than this. So there will be total internal reflection of light inside the diamond, and because of that, diamond appears sparkling. Then fourth use is mirage formation. Mirage formation, looming. Mirage is an optical illusion of water in deserts. Inverted image of an object along with the object is observed in hot day. This is called mirage formation. Formation of inverted image of an object along with object that is observed in hot day, especially in desert. This is called mirage formation. Because as you know, suppose this is the ground. So in hot day, ground is very hot. So air near ground is very hot. Hence it become less denser. And as we go above the ground, temperature is low, hence air is more denser. So you can say that refractive index of upper air is larger than refractive index of lower atmosphere. So when light goes from upper atmosphere to lower atmosphere, it is going from denser to rarer medium. So as it goes from denser to rarer medium, it bends away from normal. So we can take this atmosphere as different layers. At one particular instant, this angle of incidence becomes greater than critical angle, and then light get reflected back in same medium. And from here it bends like this. So light which started from here moves like this, and then it start moving upward. So the light which is coming to eye of observer appears to coming from here. So this observer going to see image of this point somewhere here. So this observer will see object as well as its image. So it is like this observer going to feel that there is water, and hence shadow of tree in water is visible. So he may feel false perception of presence of water here near the tree. So that is called mirage formation. Now next is working of optical fiber. Optical fiber is a transparent fiber which has a core, central core, and its surrounding. This is called cladding. A light enter into it, and it is being internally reflected like this. So light travels with the speed of light, you can say, signal travels with the speed of light inside this, and there occurs total internal reflection. So use of optical fiber, it is used in endoscope device used by doctor. It is used in telecommunication. Audio and video signals are sent through this optical fiber for a long distance. It is also used to transmit image of an object. It is used to form toys, you can say. For example, pot containing fountain of fibers. Next use is rainbow formation. There is total internal reflection. or internal reflection, you can say. First, who can see rainbow? Suppose this is an observer. If he is looking on this side and sun is in his back, then he can see rainbow. So sun should be in back of observer. This is front of observer and this is back of observer. You know, these are the raindrops. These are the raindrops. These two raindrops I have shown. Suppose this is a light enters here in raindrop, get internal reflection here and finally comes out. And suppose this is red color of light and finally received by this observer. From this raindrop, after internal reflection, light come out of the drop, and suppose this is violet color. So all other color will be present in between these two. So all 7 color is being present in between these two, and this will be like an arc. Outer color will be red and inner color will be violet. Rest color will be in between these two. This is called primary rainbow, in which only one total internal reflection takes place. And in this case, this is called horizon. The violet color is at 40 degree and red color is at 42 degree from horizon in case of primary rainbow. Primary rainbow is brighter rainbow. And sometime there is also secondary rainbow visible. Here too there is total internal reflection, but here there are 2 times total internal reflection inside raindrops. And then red and violet color light comes and finally goes to eyes of observer. But here order of color is reverse. Inner color is red, outer color is violet. Inner color is red, outer color is violet. In case of primary, inner color is violet, outer color is red. So red of primary and red of secondary both are near to each other. Remember this thing. This angle is 51 degree and this angle is approximately 53 degree, you can say. So these are the angles for secondary rainbow. So in primary rainbow there is 2 refraction, 1 internal reflection. In secondary rainbow there are 2 refraction and 2 internal reflection. 2 refraction, 2 internal reflection. Here 2 refraction, 1 internal reflection. This is less brighter, this is more brighter, and it looks like this. Like this. Suppose this is primary rainbow. This is violet color, this is red color. This will be secondary rainbow. This is red color, this is violet color. So red color of both rainbows are facing each other, you can say. This is secondary rainbow. Secondary rainbow. And this is primary. So to observe rainbow, sun must be behind you. So this you should remember. Now in case of total internal reflection, working of optical fiber, I'm going to give one illustration on this. So regarding optical fiber, I'm going to tell one more thing. Suppose this is optical fiber in which there is a transparent core and there is also a cladding. Refractive index of core is N1, refractive index of cladding is N2, and N1 is greater than N2, means this core has more refractive index as compared to cladding. Cladding is covering. Now suppose this is normal and this is air. If I incident light on this, then after refraction it goes like this and get incident at core cladding interface and this will be angle of incidence here. If it is angle of incidence, this is angle of refraction. Now, if I increase angle of incidence, if I increases R also increases, and see, let this angle be I naught. Angle of incidence at core cladding interface is I naught. Then this angle is 90 degree, this angle is R, this angle is I naught. So here from triangle we know that sum of R and I naught is a constant. R plus I naught is constant, and that is 90 degree. So if R increases, then I naught decreases. If R increases, then I naught decreases. And here there should be total internal reflection. So minimum angle this should not be less than critical angle. If it is critical angle, light will go like this. So I naught minimum must be equal to C. And I naught minimum we can write, I naught we can write 90 minus R. So here we can write 90 minus R maximum, because when R is maximum, I is minimum, is equal to C. So from here R maximum is 90 minus C. So maximum value of R is this, and if it is maximum value of R, then maximum value of I should be this. Suppose this R is now 90 minus C, so it is maximum value of R, and if R is maximum, then this I is also maximum. So up to here, if your angle of incidence is up to here, light will not leak into the cladding. If your angle of incidence is more than this, then here angle will be lesser than critical angle, and a refraction will take place, means light will go from core to cladding. So if you want that light should not go from core to cladding, then this I naught should not be less than C. So minimum value of this should be C. So maximum value of this should be 90 minus C. So maximum value of this should be I max. And this I max is said to be maximum value of angle of acceptance up to this angle. And you know, it is a conical angle like this. This is a conical angle like this. So if light is incident in this region, it will be, you know, transported through optical fiber. Otherwise, if your angle of incidence is more than this, then light will go from here to here, and finally from cladding to outside of fiber. So light will be leaked, you can say, signal will be lost. So our angle, maximum angle of incidence on optical fiber should be this. This is called angle of acceptance. Angle of acceptance. So calculation of angle of acceptance means maximum angle of incidence. This we are going to find. Now I am going to use Snell's law at this point. So it is 1 refractive index of air into sine I max is equal to N1 into sine R max, that is 9 R maximum, and that is 90 minus C. So sine angle of acceptance is equal to N1 sine 90 minus C, and sine 90 minus C is cos C. So sine angle of acceptance, maximum angle of incidence is called angle of acceptance, is N1 into cos C. Now we know that sin C refractive index of rarer medium to that of refractive index of denser medium, so N2 upon N1 in this case. So cos C under root 1 minus sin squared C, because sin squared theta plus cos squared theta is equal to 1. So cos C is 1 minus N2 squared upon N1 squared. So it is N1 squared minus N2 squared upon N1. This is cos C. So at place of cos C we can write this. So sine of angle of acceptance is equal to N1 into under root N1 squared minus N2 squared upon N1. N1 cancel. So I max, that is angle of acceptance, is sine inverse under root N1 squared minus N2 squared. So this is maximum angle at which you should incident light on optical fiber here, so that there is total internal reflection occurs at core cladding interface. Theoretically your angle of incidence should be slightly lesser than this. Then proper total internal reflection will take place at core cladding interface and light will propagate inside the optical fiber. So our angle of incidence should be slightly lesser than this. So that is, this angle is called angle of acceptance.